Good. Hello, everybody. Good morning, everybody. I understand it's very difficult to start so early after the banquet and after all the posters. I would like to start by thanking the organizers for this opportunity to speak here and bring all these beautiful München, and not only people from München here. And before I start, I was spending sabbatical in Munich, but I'm not coming from Munich. I came from University of Minnesota. It's on the Mississippi River in Minneapolis, and nowadays it looks like this. But I bring this slide, maybe Minneapolis doesn't sound familiar for many of you, but next March meeting is going to be in Minneapolis, and it will not look like this, but maybe like that. So if you go to March meeting next year, be prepared. And with that, with no further delay, let me introduce the topic of my talk. And this is Kitaev quantum spin liquid. So this model, it's an Ising interaction. So it's a honeycomb lattice that was proposed by Alexei Kitaev in 2006 on the honeycomb lattice. And it has some Ising interactions on different type of bonds. Nowadays, many people heard about this model. And this slide actually intended to be both the introduction and kind of take-home message. So this model is exactly solvable or 2D model, and the ground state of this model is quantum spin liquid ground state. And it's a rare case, and that's why it's also very beautiful. And another important thing about Kitaev model that it can be realized in real materials, and by nowadays it's the whole field. So the first suggestion how it can be realized was done by Georgia Kelly and Ginyat Khaliuddin in 2009, and in 14 years, we have the whole table. You will see them later. And because it has, from one point of view, an exactly solvable ground state, and from another point of view, it has all this experimental realization, I think it's an excellent playground for theorists and experimentalists to study quantum spin liquid properties, which otherwise are quite difficult to study. And finally, and that's probably related to what we heard last couple of days, it has a potential. It was proposed to be a potential solid-state platform for quantum computation. So that was the idea of Kitaev behind proposing this model. So to some extent, this is the home-take image, and I will try to elaborate on the way. So, and I know for some of you, quantum spin liquid is a very familiar concept, and you probably work on this, so I apologize in advance for some introduction, but maybe there are some students for whom it will be important. So let's ask the question, what is quantum spin liquid? And nowadays, if we have a question, what we do, we either say, Alexa, what is quantum spin liquid? Or we choose our favorite AI. So let's ask ChatGPT. So if you ask ChatGPT, make a poetry, I want to be poetic, so let's have a poetry about quantum spin liquid, then that's what you get, and it's actually not that bad. So I cannot do better than that for sure. So it's kind of English style poetry that was by design. Let me start reading, I will not read the whole. In a world so small and fleeting, where particles are constantly meeting, there is a state that's quite unique, a liquid with a spin so slick. Quantum spin liquid is its name, a state that's both liquid and tame, where spins are free to roam in a dance that never home. In this liquid, there is no constraint, spins can move and flip without restraint, a dance that both chaotic and free, a state of matter that a mystery, and so on. Okay, so not bad. But in fact, it answers to most of the question about quantum spin liquid. So indeed, it's quantum because spins are small and fleeting. So slick, spin 1/2. And then indeed, it's spin liquid, and spins can move, flip without restraint, not ordered. So it already gives us some idea about what is quantum spin liquid. That's about, like, once again, Alexa/AI. But if we want to understand it a little bit better from scientific point of view, let's ask other authorities. So who are authorities for the theories? Okay, let's start from one. Okay, so let's try to demystify it a little bit. and other authorities, so if we would ask Landau, okay, so what Landau? Quantum spin liquid did not exist or was not formulated at that time, but if we ask him, he would tell us that it's something what he didn't classify in his Landau paradigm. So quantum spin liquid, according to Landau, would be a state of interacting spins that break no rotational or translational symmetry, because according to him, all magnetic or in principle orders can be characterized by a symmetry which is broken, okay? So with that characterization, we can go further, and when they think about magnetic states of matter which quantum spin liquid is not, then we can think about some simple ferromagnet. So in this case, if we go to very, are you sure? No. Sorry. Oh, no. Okay, yes, I know that I should check sometimes here. So in the high temperature, when interactions are kind of small compared to the temperature, then ferromagnet, what kind of symmetry the ferromagnetic ordered state will break. So it will break rotational symmetry, because below some symmetry we will have like all spins looking parallel, and that can be easily characterized with the help of Landau paradigm. And now, okay. So another simple example is antiferromagnet. So again, in the case of the paramagnet magnetization, which would be the order parameter in ferromagnet, is still not zero, but we can define another order parameter that would be the difference between magnetization of two different sublattices, and still we can do the same thing, and in that case, both rotational and translational symmetry will be broken, and so on. I can go to some spiral states and some more complicated states, but I can always use this paradigm, and in that sense, the definition of quantum spin liquid would be the state which is not breaking any symmetry. And in that sense, I can also make a comparison between the magnetic states of matter and the states of water. So in that case, ferromagnet, antiferromagnet, or some other states, magnetic states, they would correspond to spin solids, while paramagnetic phase, where the spins are fluctuating and non-interacting, will correspond to spin gas. And in that sense, it should be something in between, and we know what is in between is the liquid, okay? So in that sense, there is a spin liquid. So once again, no symmetry was broken. So next authority for theorists, so let's ask Anderson. And actually, Anderson was the first person who introduced this concept in a modern condensed matter. So, and actually what his idea, so he was working on a different problem. It was about the triangular lattice and the state resonance valence bond state for triangular lattice, which he proposed as a ground state, was not the ground state. We know this. But we can think about some lattice with antiferromagnetic interaction where the lattice can be covered by spin singlets, and what is important for this state that it's a really superposition of all possible covering. That's a resonance valence bond state, and basically if I would ask what is the definition from Anderson, he would say, okay, this is the state which cannot be written as a product state. It needs to be a superposition, and all the interesting properties of quantum spin liquid comes from that, not breaking any symmetry, and that the state cannot be written as a product state. So when we look for quantum spin liquid, we usually look in some frustrated magnets, because then there are strong quantum fluctuations and the magnetic order can be evaded. This is the parameter which usually characterizes the level of frustration. It's kind of Q-revised temperature, which characterizes the strength of interaction and the ordering temperature. And if this number is very, very large, then we say that the system is frustrated. Okay? So, and if I want to give a little bit more specific, there are two basic ingredients for realization of quantum spin liquids besides the gauge structures, and I know some of you are studying this. So what you need to have an extensive number of the state with the basically better the same lowest energy or close to that low energy, and that will be manifold from which we will do this classical state and from which we will form this superposition state. And then it's not enough to have very high degeneracy, we also need to have a tunneling. These two things are absolutely essential gradients to have a quantum spin liquid state. Okay? So so far, I was mostly giving you a negative definition of quantum speed liquid, but if I go to experimentalists and say, okay, find me something which is not that, that's not specific enough, so we need to give some positive definition. And basically, nowadays, after so many of research, people can characterize quantum spin liquid with a definite properties, and one of them can be topological order and long-range entanglement, but we can also define that if you have a quantum spin liquid, then excitation will be fractionalized. So I will not go to the detailed explanation of what is this, but many of you are doing numerical research, and then you know that you can compute the topological entanglement entropy, and then basically this different from the error law would be non-zero for topologically ordered state. To some extent, that can be considered as equivalent of order parameter in Landau sense, but now it's kind of a topological order, or there is a topological ground state degeneracy. And then there are fractionalized excitation, which can have also some particular anionic statistics. So I will talk about fractionalization in a moment, but what I want to say that these two is very difficult to check in the experiment. Maybe in the cold atoms or these new quantum simulators or studying of the small system, you can do this, but historically, so far, it was mostly done with the numerical methods, and actually people learn a lot about quantum spin liquids by doing very sophisticated numerics. And perhaps using the quantum computer, which you heard like other days, would be also useful for characterizing quantum spin liquid. But if you want to think about the experiment, then that's not an appropriate way of thinking, because I don't think that you first can prepare a two-dimensional quantum spin liquid and then put it on the torus. That would be really a big sophistication. So fractionalized excitations is what can be probed in the experiment, and there are many dynamical probes which can tell us something about quantum spin liquid. Okay, as I promised, another important message, take-home message, when people talk about quantum spin liquid, you should ask what kind of spin liquid. So maybe at the beginning, that was enough to give this negative definition, and then it was just the class of materials which you can call, or class of the model, quantum spin liquids. But nowadays, we understand that there are many different quantum spin liquids, and they have different characteristics. So Kitaev models, the gapless or gapped quantum spin liquids, it's only some of them. And there are actually not one originally proposed, but nowadays it's a variety of them. Okay, so how to look to quantum spin? As I said, we look to to excitations, and therefore we can look to the signatures of fractionalization in the dynamical probes. This is not the full list of the probes which can be used. Now people are trying to think for more and more different new probes and also nonlinear responses. So, but what is important to understand that if you look to the probes which can be understood within the linear response theory, then since excitation carry fractional number, fractional in the sense that the original excitation is spin flip, which can be characterized by magnon, and this is S equal 1 excitations. And then if they're fractionalized, then we can have a spinons fermionic excitation with spin 1/2. Then response from quantum spin liquid is always a multi-particle continuum. The problem is that multi-particle continuum can be very different, and we need to extract information, for example, like shape, but also the temperature dependence, and you clearly see that the temperature dependence on this, and that continuum would be completely different. And being able to characterize this continuum of excitation quite precisely is important to understand quantum spin liquid. And what is important, non-universality. There are many different spin liquids. They will have a different continuum and different properties of continuum. That's important. So just very briefly, fractionalization can be the easiest to understood in 1D. So if I consider 1D chain, so like antiferromagnetic chain like this, and then, so here all the bonds are antiferromagnetic. I flip one spin, and basically by this I create two-domain walls. I can describe these two-domain walls with the spinons, because the flip is spin 1. Now I have two particles that spin 1/2, and these spinon excitations, they can move, and that is the question about confinement or deconfinement phases. But what is also important, that there are no examples of quasi-1D system where analytical calculations which are possible in 1D can describe what was observed in neutron scattering, and this continuum was studied in neutron scattering in a pretty good way. So this is basically the continuum, and this excellent quantitative agreement between experiment and theory tell us that we do understand this continuum in 1D. The problem is that when we go to 2D or even 3D, because Kitaev allows us to describe spin liquids also in 3D, quantum spin liquids arise in the strongly correlated system, and you all know that it's very difficult to treat exactly or treat faithfully the strongly interacting system beyond 1D. So in that sense, it's bringing me to the topic of my talk, because Kitaev quantum spin liquid is both a strongly correlated system, but because it's exactly solvable, we can do calculation, and therefore we can compare what we compute with what experimenters observe. At least we can guide that if it's close to quantum spin liquid, then that's what you should expect. Okay? So once again, this is the slide about Kitaev spin model, and the excitation in Kitaev spin liquid, the fractionalized excitations, are different from the spin-on in 1D chain, because the spin flip create, so in 1D, spin flip creates two identical spin-ons. And therefore, you have absolutely the same fractionalized excitation. So here you have a two type of excitation. You have a flux pair, so you create a flux. So basically, what Kitaev did, he understood the property of proposed model in terms of the Majorana fermions using Majorana representation. So once again, I will say two words in a moment, but what's important that you can create the fluxes, and fluxes, Z2 fluxes, they are static, and that is explaining why the model is exactly solvable, but they're also gapped, okay, in the pure Kitaev model. And then you have a Majorana fermions, which depends actually if these all couplings are the same or not. They can be gapless or gapped. And these models can be easily generalized to 3D lattices. Then you have, for these Majorana fermions in 3D Kitaev model, all variety of band structure for the Majorana fermions. And that's make this field quite rich. Okay, so just very quickly, so once again, when I talk about Z2 fluxes, this is defined by this plaquette apparatus WP, which can be defined at each hexagon. This is a particular product of spin 1/2 from outgoing bonds. What is important that each of these operators commute with the Hamiltonian, so it's a conserved quantity. They also commute with each other, so we can characterize all the sectors, all the excited states by the flux numbers. And what is important, in the ground state, all these fluxes should be +1. And this is basically the mapping of spins to the Majorana fermions, which we all know. Okay, so as I said, so these are these plaquette operators. They can, cancel. So they can be rewritten, this plaquette operator, in terms of these link variables, which is just the product of the particular Majorana fermions on the bond. And this is the emergent Z2 gauge field in this problem, and the eigenvalues are ±1. Okay? So once we know that these are all static variables, we can fix it, just numbers. We can put ±1. So we distribute them. Then our Kitaev model is nothing else as the hopping for the other Majorana fermions. And that is the reason why it is exactly solvable. So basically, it has a macroscopic number of conserved quantities. Okay? Okay, so one more thing, when we have, so that's kind of a picture about the fractionalization. So here in the ground state, all fluxes are +1, and that is determined by this WP = 1 and this yellow plaquettes. And if we do the excitation, they are gap, and we put them in red, and that corresponds to this value -1. And this is for 2D lattice, the dispersion for Majorana fermions, and you see here the familiar Dirac cone, which also appear in the studies of graphene. Okay? So now we understand what is the model. So next question, so how it realizes in real materials, okay? So if it realizes in the real materials, maybe we will have another playground to look for Majorana fermions, you know? Okay, so without details, the first proposal comes from Jackelli and Haliulin, and basically what they tell you that you need to have not spin 1/2 degrees of freedom, but pseudo-spin degrees 1/2 degrees of freedom, because they need to interact in an anisotropic bond-dependent way. And for spin 1/2, that would not be possible because it will violate this SU2 symmetry for spin 1/2. And therefore, in order to have this pseudo-spin 1/2 degrees of freedom, you need to have a strong spin-orbit coupling and this proper free coordination. So basically, they suggest of what kind of material we should look to look for the Kitaev interaction and possible Kitaev spin liquid. Okay, so as I said, from the moment of their proposal to nowadays, it's 14 years. And many reviews. So if you look in recent years, there was many reviews. Some of them are experimental. So I just mentioned only these two. But you see that there is a big list of materials which are studied with respect to Kitaev spin liquid. And what is important, and Simon Traps actually divide them in two categories: first generation Kitaev materials and the second generation Kitaev materials. So in the first generation of Kitaev material, you always have some long-range order, because nature is not too kind for us, and it always gives whatever is symmetry allowed, and in these materials there are other interactions, smaller than Kitaev interactions, but they're still allowed, and they give us, this is like the list of the materials, and then you see in the specific kit that there is a peak. So basically they order. What is important that they are still frustrated. They order at the temperatures. So for example, the famous alpha ruthenium chloride orders at 7 Kelvin, while the Kitaev interaction is of the order of the 100 Kelvin. So you clearly see the frustration. And then the second generation of Kitaev materials, they have a bit more disorder of unknown or known type, and they sometimes don't know, and the most famous material is this hydrogen intercalated lithium iridate. And then, of course, there is a question to theorists and to experimentalists to understand these materials which do not order. Do they just simply disordered system, or do they still keep some features of the quantum spin liquid and some entanglement? Okay? So, and the key question which basically we are trying to answer is, can we observe a simple Kitaev physics and maybe catch Majorana fermions physics in realistic materials where we do have these complex low-temperature magnetic orders? I didn't discuss of what kind. In many of them are zigzags, but in some of them the order is more complicated, and these complex magnetic orders come from these other terms which are allowed by symmetry. Okay? So, and this is kind of the general way of thinking about this. So here is this strange perturbation. I will call this ... perturbation, and this is the pure Kitaev model. And what I know that if the temperature is equal to 0, I have this beautiful solution. But because the Z2 fluxes are gapped, I do have a stability in the temperature of this before my fluxes get populated. So here is the 0 flux Kitaev spin liquid. But then, even when the fluxes get disordered, so I have a proliferation of the flux degrees of freedom, up to the energy scale corresponding to the Kitaev interaction, which is roughly speaking, Kitaev is around 100 Kelvin. So then I have a flux disordered, but I still have this fractionalization. And above of this, it's a usual paramagnet. What is important that if the perturbation is small, yes, there is still this gap which protects my Kitaev spin liquid with respect to magnetic order. So I increase the strength and its order. But if this perturbation is still weak, then the ordering temperature that would correspond to the ordering temperature, this solid line, is still very low. And then, if I do my dynamical probes somewhere here, I do them at finite energies and finite temperatures above the near temperature, then in my dynamical probes, I will see mostly the effect of fractionalized excitations. And that is the whole idea behind why people can use the dynamical probes still to obtain the information about quantum spin liquid. Okay, so next question is how Kitaev quantum spin liquid look in dynamical probes? And the answer is depend on which probe. And let me give you 5 examples. I don't know if I'll have time, 5 minutes, 1 minute for example probably is too much, but the first one was suggested in elastic neutron scattering, and basically in this case, and that was the work from Johannes Knolle. So they will propose that in a dynamical structure factor, you will, this is from this paper of 2014. So in the dynamical structure factor, first of all, because you create at the same time the flux, which is gapped, and then Majorana fermion on top of this, then you will see almost non-dispersive response with the gap, and this gap, this flux gap is around 0.26 of the Kitaev interaction. And then, indeed, Newton scattering experiments were performed, compared with the prediction, and one can say that like this continuum coming from the Majorana fermions was observed. It was still a lot of contradiction. Is it not a 2-magnon continuum or it's a Majorana fermion continuum? But it was some progress in understanding, especially in the magnetic field. So another example which we proposed in the same year together, so in 2014, was to use an elastic Raman scattering. You know, Raman scattering is a Q=0 probe, but contrary to neutron scattering, so if you look to the Raman operator, it's photon in, photon out, so you can write this Raman operator, and what you see that it's proportional to the Hamiltonian on the bond. So actually the flux operator would, or this U variable commute, the Z2 gauge will commute with the Hamiltonian, and therefore Raman operator will only excite Majorana fermions continuum, and then one can study how this continuum will be modified if you are not in exactly solvable point, but if you have a little bit of Niel interaction here, or you have a gamma interaction. That's an interaction which are characteristic for the material. Okay? So once again, this is the example, and now there is more experiment about alpha ruthenium chloride, where the Raman scattering by the Köln group, for example, is done in the magnetic field, but the continuum was observed, and it has some, at least qualitative agreement with the predicted theory. This is the 3-dimensional Kitaev material gamma iridate, and again, some features of continuum were observed. Okay? So example 3, once again, I'm a little bit hurrying up, is Raman is Q=0 probe, but the question is, can we have a map of this continuum in the momentum and energy space? For that, we need to have a momentum resolution, and that's what is provided by RIX by inelastic X-ray scattering. So, for example, in iridates, that can be understood with the LH, and in that case, so photon comes with it's an X-ray, it comes with a very high energy, so it creates the excitation, it's take the electron from the 2p level, very deep from the core level, and then bring it up, and then it creates a core hole. So basically then the momentum Q and the energy omega is put into the Kitaev model. Once again, this is how the RIX intensity will be computed, and the scattering amplitude, which is written here, so it can be decomposed in 4 fundamental channels, and it's we can look channel by channel, and if eta is equal to 0, so it's just identity matrix, then there is no spin flip. In the no spin flip channel, then we will look only into Majorana fermions, and we look at this, and basically what you can get a prediction for what should be observed, and this is at 0 temperature, and for example, you can see that a very characteristic feature which you can relate to the symmetry in the Kitaev model is the absence of the single at a gamma point, and then you can also see what is the shape of this continuum and how it evolves with the temperature when both Stokes and anti-Stokes are nearly symmetric. Okay, I understand my time is over. I just flashed the slides. Phonon dynamics can also be used, and one of the examples is the sound attenuation, and in this case you just bump acoustic modes into the quantum spin liquid, and you look how they attenuate, and basically you can do the analysis. But what is important, so we predict what are the characteristic features of that, but let me tell you that the experiment was done, and in fact in alpha ruthenium chloride you can see that longitudinal modes and transverse mode attenuate in a two different way, and you can really connect these with the processes which are happening in the Kitaev spin liquid. So I recommend you to look to that paper if you are interested. And then another example, number 5, is the inelastic scattering tunneling spectroscopy. So it was first again proposed by Johannes Knolle group just to look to some age mode, but it can also use when we have a vacancy, and the vacancy tunneling spectroscopy also can produce you a very characteristic features, because vacancy induce a low energy mode. That is schematic picture of the vacancy induced mode. And now, so basically the current, which you will see di over dv, would be proportional to, again, to dynamical structure factor, and once again one can say something definite about what is seen. Okay, this is really the last slide. So very briefly, I just want to give you all these kind of methods. I understand that I cannot convince that each of them give you, but all together, they give you a combined evidence. So then you can, because you can do prediction, and then you can look to experiment, then you can see if this material is really close to Kitaev spin liquid or not. And over the years, I was collaborating with different people. Let me acknowledge them, and thank you.
All right, Natalia, thanks a lot for this great talk. We do have time for a couple of questions.
Natasha, all condensed matter probes are essentially two-point probes, like current, spin, but with cold atoms, you can do multi-point correlation functions. So let's say if we could access multi-point correlation functions, could we get more convincing evidence of spin liquids?
Yeah, I think instead of continuum, so in all these kind of non-linear responses, you can get some you can have some sharp features, you know, kind of due to, if in a very simple word, due to interference effect. But in the non-linear responses, non-linear susceptibility and so on, you can have some definite features, you know, not a continuum which you need to decompose. But usually the problem is that these non-linear responses are weaker, or maybe in cold atoms, once again, then you can engineer a quantum spin liquid, and then you can study its properties, but it's not in real material, so you're really probing what you engineer. In real materials, there is always something else is going on, and these nonlinear responses is usually weak. Now it's 2D terahertz coherent spectroscopy, which Peter Armitage is proposing. That is one of the way, but they still didn't see anything definite in rotating chloride.
Any more questions? I don't see any right now. Then let's thank Natalia again.